carbon fiber?
Carbon fiber, as you might have guessed, is a material made out of carbon fibers. These fibers, which range from 5 to 10 micrometers in diameter, are bundled to form what is called a tow, which is either used by itself or is woven into a fabric-like sheet. In most cases, carbon fibers are combined with resin to form carbon fiber reinforced polymers. When people refer to carbon fiber, they are usually referring to these polymers. Carbon fiber has a wide range of desirable characteristics, including high stiffness, high tensile strength, low weight, high chemical resistance, high temperature tolerance, and low thermal expansion. With all of these incredible properties, carbon fiber is a dream come true for many of today's design engineers. We're talking airplanes, spacecraft, high-performance cars, bikes, golf clubs, even race-quality rowing oars. That being said, carbon fiber wasn't always so awesome. I'll give you a brief history to show you what I mean by that. Thomas Edison actually created the first carbon fiber filaments in 1879 by baking cotton threads for his first incandescent light bulb. But he got so caught up in the whole electric light thing that he didn't go much further. These filaments were improved for a few years until they were replaced by tungsten in 1906, making carbon fibers pretty much obsolete. It wasn't until 1958 in Cleveland, Ohio that Roger Bacon accidentally rediscovered carbon fiber while trying to measure the triple point of carbon. During these tests, he observed filaments growing on the negative electrode of his arc furnace, so he included them in his published documents following research. Because these crystals were grown in argon at a pressure of 92 atm and a temperature of 3900 K, he estimated that the production cost would be about $10 million per pound. That's about 17,000 times the price of gold at that time, just to put it in perspective. Needless to say, the price had to come down before people would even consider potential uses. Enter Dr. Akio Shindo of the Agency of Industrial Science in Japan. He was the first to make carbon fiber with polyacrylonitrile, which for everyone's sake we will refer to as PAN, or PAN. PAN is a synthetic, semi-crystalline organic polymer resin. If that means nothing to you, just know that it allowed Shindo to produce a carbon fiber with 55% carbon in a much more cost-effective manner than Bacon's, which only contained 20% carbon. While this was a great development, the technology wasn't truly considered for its potential until 1963, when British scientists Watt, Phillips, and Johnson patented a manufacturing process for PAN through the UK Ministry of Defence. Various companies and governments jumped on the bandwagon, though with varied success until the 1990s and 2000s, when skeptical, metal-loving design engineers finally realized that carbon fiber had a place in the future. With increased funding, fibers with up to 95% carbon were produced, yielding the incredible strength-to-weight ratio carbon fiber is known for today. Simultaneously, the price per pound has dropped, allowing for the gradual but steady increase of carbon fiber uses today. Without further ado, I'll pass you on to my good friend Matt, who will talk more about the manufacturing processes of carbon fiber today.
Carbon fiber production begins with what is called a precursor. The precursor is generally an organic material characterized by long molecular chains bound by carbon atoms. About 90% of all carbon fiber products are made with polyacrylonitrile, or PAN, as the precursor, where the other 10% come from substances such as petroleum pitch or lignin, the organic substance in trees that is responsible for binding cell walls together. Much of the PAN precursors used in the United States production are imported from countries in Europe and Asia. The precise composition of precursors vary from one company to the next. For exact processes is considered trade secret. We were unable to uncover these secrets in the making of this video. The manufacturing process for carbon fiber is much a mechanical process as it is a chemical process. On the mechanical end, it involves the fiber being stretched over hundreds of feet, winding through the manufacturing plant around hundreds of spools, ultimately stretching its diameter to fractions of its original size. Resulting diameters range from 5/1000ths of a millimeter to 10/1000ths of a millimeter. That's about a tenth of the thickness of a standard piece of printer paper. Next, the fibers are sent through an oven for the oxidization process. The oxygen molecules in the air combine with the fibers and cause the polymer chains to begin cross-linking. This is the most time-consuming stage of production, and it is the process that gives carbon fiber that ebony shade we know and love. After the oxidization process, the fibers undergo another heating process called carbonization. The fibers are sent through a specially designed furnace that progressively increases the internal temperature, with entrance temperatures ranging from 500 to 700 degrees Celsius and exit temperatures ranging from 1200 to 1400 degrees Celsius. I know what you're thinking. What is so special about this furnace? I'll tell you what. The furnace produces an oxygen-free atmosphere for the fibers to pass through. At the entrance and exit of the furnace are what are called purge chambers, which prevent oxygen from entering the furnace. With no oxygen and no combustion, the high heat violently vibrates the atoms in the fibers, expelling the majority of non-carbon atoms out of the fiber. The result? A long and tight chain of carbon atoms with only a few non-carbon atoms remaining. The resulting fibers are smooth as silk, but do not bond very well to the epoxies and polymers commonly found in composites. To increase bondage, the surface of the fibers is slightly oxidized. This process varies from manufacturer to manufacturer, but some commonly used fluids are carbon dioxide and air. The addition of oxygen molecules increases the polarity of the fibers, yielding better chemical bonding properties, as it also roughens the surface, yielding better mechanical bonding properties. This is a delicate process, for too much oxidization can create tiny surface defects that could cause the fibers to fail. After the surface of the fibers is treated, the fibers are coated to protect them from damage during packaging. Common coating materials include epoxy, polyester, nylon, and urethane. They are then wound onto spool-like cylinders called bobbins and are shipped across the world to be used by secondary manufacturers.
The future of carbon fiber. Over the next several years, the global carbon fiber market size is forecasted to have an annual growth rate of 17%. Reaching 118,000 tons, with an estimated market value of $7.3 billion by 2017. The future of carbon fiber is in every field that has an interest in making products lighter while increasing strength, from car body panels to wheels and drumsticks to turbines and spaceships. Koenigsegg is in the process of developing seamless carbon fiber wheels. The wheels are the first to be manufactured entirely out of carbon fiber. The wheels are the most important part of the car to have very light, since the effects of acceleration and deceleration of the car act most strongly on the unsprung mass of the wheels and other parts of the drivetrain, like the drive shaft. The drive shaft of a car has already been manufactured as a carbon fiber part for several years, and marketed as an aftermarket mod for most performance vehicles. The special feature of the carbon fiber wheels is that the barrel, spokes, and hub of the wheel are all hollow to reduce weight. The process for manufacturing this while keeping a very high stiffness is proprietary information of Koenigsegg and isn't available to the public. However, from their video, it looks like they use the traditional method of layering, very similar to fiberglass. One of the most exciting parts about the future is being able to make whatever you want using a 3D printer. The drawback has always been the low strength of the thermoplastic used by most additive manufacturing printers. I say most because a company called Markforged has just released a 3D printer called the Mark I that is capable of matching any shape constructed from a normal 3D printer, but using carbon fiber as the build material. This is an incredible step forward for the future of additive manufacturing. Instead of limiting the use of 3D printing to prototypes and low-stress parts, the resulting pieces are stronger than 6061 T6 aluminum by weight. The secret is, instead of using long, continuous spools of thermoplastic injected from a feed head, the Mark I uses long, continuous strands of carbon fiber and a special resin they developed, again proprietary knowledge, to lay down layer upon layer of the material. The printed part requires no cure time and is ready to be tested as soon as it can be lifted from the test bed. The applications for the parts produced by 3D printing carbon fiber will change the way everything from turbine blades to car wings is manufactured. So why isn't everything made out of carbon fiber? Money. As of today, carbon fiber costs about $10 per pound to produce. Steel, on the other hand, costs less than $1 per pound. Now you might say that steel is much heavier than carbon fiber, and you'd be right. But analysts say that in order for carbon fiber to become widely used in the automotive industry, the price per pound will have to come down to around $5. This explains why carbon fiber has been limited to the performance sector of the auto industry. However, things are looking up. 10 years ago, the price per pound of carbon fiber was $150. If we follow that trend, we should be hitting our projected 118,000 tons by 2017. So be prepared to see a lot more of the futuristic checkerboard material in the next few years. Thanks. Three D printer.